Hello, everyone. This is Sadoghi, CS faculty at UC Davis. Welcome to Reimagine 2020 Global Blockchain Conference. It is my pleasure to be here on behalf of my research group, Expo Lab, to talk about our vision and research centered around blockchain. In particular, today, we're going to talk about ResilientDB, and that is our experience in building a global scale, privacy-preserving blockchain fabric. And with that, let's get started. First and foremost, I would like to thank my talented and creative students, starting from Yella Helling, who's my postdoc student, and has been focusing on complexity analysis of fault-tolerant protocol. Suyash Gupta, my senior PhD student, has been looking at consensus as a meta protocol, so just going beyond a single BFT algorithm. Tamir Ghada has been looking at coordination-free concurrency and distributed transaction, also my senior PhD student. And finally, Sajjad Rahnama is halfway through his PhD and has been focusing on global scale consensus. I also have a set of wonderful master and undergraduate students. Dhruv, Priya, and Rohan has been looking at sharding and consensus, and Shubham and Shinyuan has been looking at consensus acceleration via RDMA in high-performance computing setting. Kind of give you a little bit of a journey where we're coming from in our work is that going back about 10 years ago, I started looking at SQL analytics. In particular, I looked at how do you accelerate warehousing solution or OLAP engines, online analytical processing platform. And we looked at the modern shift in hardware, and the one space that we really focused on is the use of FPGA and hardware acceleration in order to accelerate by a factor of 10 or 100x our analytical execution. And this is a work that has been going on fruitfully for the past 10 years. Alongside of it, we started also looking at transaction. We look at how do we improve our transactional engine using variety of indexing technique and focusing on high-dimensional indexing. And again, this is the work that has been going on for a long period as well too. In terms of transaction, we didn't just focus on indexing, but we also started looking at the core, which is the concurrency protocol. And we have developed several concurrency techniques over the years, but the final piece that we have looked at is with my student Tamir Ghada, is that we asked a very profound question. Knowing that concurrency is the main bottleneck of any transactional system, we asked, is it possible to eliminate concurrency coordination altogether during the execution? And the techniques that we've developed, it's called a QCC, a queue-oriented planning and execution paradigm, in which we have a set of worker threads that in parallel and independently take a subset of the transaction and they plan them. And this is followed by the second phase of having a set of execution threads that now take a set of operation gathered from the transaction in the planning phase, and again in parallel and independently without any coordination or minimal coordination, they execute. This work appeared at Middleware 2018, and it also won the Best Paper Award as well. The other point that sort of you may have already noticed is that we talked about SQL analytics and SQL transaction as sort of two independent entities. But in practice, although it's essential to run the day-to-day tasks, we need to have these operational databases. We need to have this transactional system. But in order to actually run an enterprise, we also need to be able to do our reporting, be able to do our analytics, to be able to figure out the sales pattern, and to be able to do our forecasting to see where the enterprise is moving toward. And that's happening in our analytical engine. But by design that we have today is that there is a gap between transaction analytics and the data needs to be pushed from one to the other. And there is a gap. And so the data that we're actually analyzing is a stale data. So around 2012, when I joined IBM Research and TJ Watson, we asked again yet another profound question. Is it possible to unify these transaction analytics and entering the HTAP at the unifying stage of a transactional analytical system? And as part of that, we developed a lineage-based storage architecture, an LSTOR, that achieves that goal. And so in doing so, we looked at every single layer of the database stack, from logging, recovery, index maintenance, trigger, concurrency, buffer pool, and this was a comprehensive work that it took about 4 years. And so several publications came out of it, and there are 34 patents protecting sort of various facets of this work that I was engaged in when I was at IBM Research. And sort of kind of moving forward is when I joined Purdue University, we'll ask another question saying, well, we've looked at concurrency, we've looked at the analytics, we've looked at the unification of the two, but at least conceptually, when it comes to a transaction, we assume that the data is going to fit in a single machine. And that was driven by the expansion of the size of the main memory. But in practice, this may not always be the case. You may want to be able to partition and shard your data over a set of a machine. And this is not just only for the purpose of be able to have the sufficient hardware to execute at the maximum throughput possible, but there may also be government regulation and mandate that forces, for example, that the data from Europe will stay in Europe, and the data in the US needs to be processed in the US. So there are other factors that advocates the need of the ability to partition data across a set of machines. So we then look at distributed transaction, we look at the agreement protocol, and one of the work that my student Suresh Gupta did was developing a technique called easy commit, which is a two-phase commit protocol without the blocking behavior. And then later, Tamir Radah extended his QCC work for queue-oriented concurrency, and now he developed queue-oriented distributed transaction execution that also exhibit the same coordination free property that the QCC had initially. And so that was a recent work that was published earlier this year. Now, kind of moving this step forward, so when I joined UC Davis in 2017, we asked yet another question, is that, sure, now we have the partition data, but how about the resiliency of it? And in the resiliency, we need to add redundancy. And we need to add redundancy in terms of the decision or the outcome of the transaction. We also need to add redundancy in the actual execution itself, because there could be failure in the execution, and there could be failure in storing and remembering the result of that execution. And this is really brings us to the resilient consensus protocol. And conceptually, they are very similar as voting protocol. And that means when I want to run a transaction, you're essentially running an election. And based on the election, based on the endorsement of the voters, you decide on the outcome of the transaction. And also, every voter or endorser in the system also maintain a copy of the outcome of that transaction. And so we're really entering a new era of computing, which we consider as a decentralized and a democratic computation. And this is yet another paradigm shift. So the earlier paradigm shift that we looked at was the ability to exploit modern hardware, whether it's FPGA, whether it's a multi-core, or whether it's a large main memory. But now this is even a broader shift of paradigm. We're looking at decentralization and democratic way of just basically computing. And this has what fueled our work in the last 3 years. And given that I've been kind of working on the concurrency for a long time, so with my friend and co-author Spiros from Ohio State, we decided to write a book on the concurrency protocol that has appeared in the last 20 years. And so we published a book called Transaction Processing on Modern Hardware by Morgan and Claypool last year. And this is something that really looks at the flourishing of the concurrency control in the last 20 years based on this shift and the availability of new hardware. And continuing that practice of sort of the educational and training and writing a second book with my students, Yella Hellings and Suyash Gupta, and we're looking at fault-tolerant distributed transaction on blockchain. So again, we're pushing the theme of transaction from your classical transaction, now looking at fault-tolerant variation of it. And the book is expected to appear later this year. And also, we've been fortunate that our work has been covered by press quite a bit, and in particular, not just the research aspect of blockchain, but also we've been doing a lot of education and training aspect. In addition to writing the books and textbooks, we're also offering blockchain courses at UC Davis. And again, since this is a new area, very little resources that are available. So I've been offering the graduate courses in blockchain, and I've also have been mentoring the blockchain club at UC Davis to allow them to have this grassroots movement for the undergraduate coming campus-wide from different domain and from different fields to come together and devise a new curriculum on blockchain and doing very exciting projects and application around it. And this wouldn't have been possible without the expertise and the generous support of Muspelt, that their focus has really been on the education, sort of the global education of blockchain. And they are also one of the main organizers for their Imagine 2020 as well too. So it's been a great work with undergraduate students along with Muspelt as well. And kind of in terms of a tangible product that has come out of our research lab is the ExpoDB. And the ExpoDB is it's more than just a database. It's a distributed, fully fledged distributed transactional database that offers also secure transaction, essentially what I'm calling the blockchain. So it has a traditional, and also it can support secure and blockchain aspect as well. So it has array of concurrency protocol, what we have developed, what the community have developed in the last 20 years. It also has an array of consensus protocol, again, what we have developed and what the community has developed in the last 20 years. And it has an array of commitment and agreement protocol. It has sophisticated toolkit for cryptocurrency. It has a mature storage layer based on the lineage-based storage architecture, the LSTOR that I mentioned earlier. And it also employs other technology in the database field, such as embedded databases as a Google Level DB or SQLite. And of course, it has a application layer that supports the smart contracts, and also a set of benchmarks, sort of standard TPCC benchmark, YCSP, and a subset of Blockbench, which is a recent blockchain benchmark that was developed by the community. And of course, there are applications. These applications are mostly developed by the blockchain club, the undergraduate student. One is the plastic coin of monetizing recycling, and one is justice to bring transparency, integrity, and accountability in the legal system in this complex multi-party system, the attorney, the lawyer, and other stakeholder in the process. And this ExpoDB itself has been not only been a research tool for us, but it's also an educational tool that over probably hundreds of students at undergraduate and the graduate level have been able to work on it, extend it, and expand it. But also, in order to contribute back to the community, we have also create a subset of ExpoDB as an open source project. And we call that open source project ResilientDB. This was something that was open source late last year, and since then we had 3 major releases. So the initial release was looking at the blockchain fabric, so extracting the fabric aspect of the ExploDB, and then the subsequent was to have more mature in-chain and off-chain memory management and storage management, and then finally our recent release has been to provide full smart contract support using Go language and pre-compilation as well, code generation to further improve the execution of the smart contract. But more importantly, we looked at the usability of the system. Of course, the graduate student, after 3 years of training, now they can run their complicated and probably have 100 different scripts in order to do this global deployment of ExploDB. But that's not something that is practical for an average user. So we now have a fully deployment web-based dashboard that allows you to fully configure every node, every replica, and deploy this to the cloud globally. In addition, we have a second dashboard that fully looks at the health of the system with all the metrics and KPIs, looking at throughput, transaction processing, the messages sent, the bottleneck, the overview of the system. So that's, again, another important toolkit that we have been adding in our latest release. Now, finally, what I would like to do is I'd like to share with you where the name came from. So, I mean, how do we come from ResilientDB, from the ExploDB to ResilientDB? And that's an interesting story, and it is a reflection of our journey as well, too. So, in the last 3 years, and this is sort of kind of expected, the moment you enter a new era, the moment you're looking at high-risk research, is that there will be going to be an uphill battle. There will be critics, there will be people that who are still unfamiliar with the new technology. They are not open to change, and so they will create pushback continuously. And so we have received a lot of rejections over the years. And as a PhD student, as a new student, this is very difficult to continuously work, pushing the boundary, enhancing your work, working around the clock, submitting the paper, and that paper or that piece of work gets rejected. But the important thing is, every worker starts from that person, that you remember that where you started it. And so that creativity was unfolded from within. And that certainty that this is the right thing to do was unfolded from within. So regardless what the critic says, positive or negative, we gather it, we see what we can learn from it, and how we can improve and simply move forward. And that creates that sense of resiliency. So it has now turned to an education of the resiliency of the student and myself. And so we became a resilient team. And then one day we were kind of talking, shall we kind of rebrand, kind of come up with a new name? And then it just sort of struck us, well, what name could it be better than this? We're looking at resilient protocol. We have become resilient in the process of developing this resilient protocol. So it is a natural to call it ResilientDB. And the first time we actually used the term was in a RealDB submission, and well, that paper is also accepted, and it's going to appear later this year in RealDB 2020. So now, kind of taking the theme of resiliency, which is core to this talk and core to my research group, is to what I consider as a quantifiable resiliency. And this is the graduate student experiments that I have ran. So I'm an avid hiker and I love to hike, and being at Davis, we are fortunate to be near Lake Tahoe and the Bay Area, and then there's just countless number of hiking trails there. This particular one is one of my favorite hikes in the area, is in Aloha Lake, Desolation Wilderness, and it's at Lake Tahoe. And it's simply a majestic landscape. As you can see on the top, in the beginning of the day, we're kind of halfway through, or maybe a third through, is the landscape is just breathtaking. And this is a pretty tough hike. I mean, this is 15 miles on a single day, 2,500 feet elevation gain. And when you reach the summit, you're looking at about 9,000 feet above the sea level. So during the day, everybody was happy. I'm with 4 of my students. And of course, by the end of the day, as you see the more picture on the bottom, well, kind of the fatigue kind of started to replace that the smile. And so kind of see, was there any failure after this, taking them on such a strenuous hike? So we'll go schedule a second hike. And the second hike is much smaller and shorter. It's only 10 miles, and it's only 1,500 feet elevation gain. But I guess few things that isn't obvious. So students are happy. They're all smiling. But the count is not quite the same as we had on the first hike. So we definitely had some crash failure, and not everybody was able to make it to the second hike. And along the way, I actually lost a student after that hike as well, too, for different reasons. But anyhow, the point is to have that balance. Sure, we are working on resiliency, and we're really pushing our work really hard as much as we can. But that the fun needs to be there. So that playfulness is also, it's essential to foster creativity. It is essential to foster a stability and resiliency. So whenever we can, we do take a sort of group hikes or a group activity that facilitate that side, and so have a balanced lifestyle. So now let's look at sort of a less of a quantifiable resiliency, and that comes up to the protocol that we've been developed over the years. So the first protocol that we looked at, which was started in January 2018, is that we said, well, again, thinking of a consensus protocol as an election, and an election has a single commissioner, meaning kind of a coordinator for that election. And computationally, one of the seminal work in running computational election is a practical Byzantine protocol, which is also known as PBFT. This was developed in '99, about more than 20 years ago now. And it considers several phases in order to reach a resilient election. But now our question was, what if we kind of revisit the role of every voter, the role of every endorser, in such a way that instead of when a voter endorses a transaction, it primarily does it based on its own local computation, without minimal knowledge of what every other node or every other node state. That means it makes a speculative decision, and that speculative decision, it is possible that is based on the wrong state of the world. And that means it needs to be reverted back at some later stage in retrospect. But the final outcome of the vote, which is the client or the user who requested that particular transaction, that invoked a particular vote, it's always going to be certain. So the state of the replica of the voter will be uncertain, and it's possible that they revert, but the state of the client is proven to always be accurate. And to doing so, we had to develop new techniques, such as allowing to do out-of-order message processing, but more importantly, this speculative execution, that the replica or the voter state can diverge. So that means their endorsement is flawed, yet the client will always eagerly find out the correct decision, and the decision that the client conclude is always a final decision. So the replica will remain in a soft commit, as kind of using database terminology, while the client will always remain in a hard commit. And kind of sort of graphically kind of showing this, so a client issue a transaction, the primary or the election commissioner inform everybody, propose this transaction to be executed, and all the voter and the replica provide support and endorse this transaction. And at this stage, the endorser, each endorser is kind of sees that the majority of endorser have said yes to this, but it is unaware if also a majority of the voter have received the majority of the support. So it only sees its own state, is unaware of the state of the other endorser. But then it is speculatively accept, execute, and send the response to the client. And now if the client sees a sufficient response, so each replica, they don't see the full view of the system, but the client, by collecting these speculative endorsement, they can paint a global picture of the system. So they are in a position to conclusively determine whether a transaction will be committed or aborted. And this is something that only in retrospect, each replica or each endorser will find out in the future. And so this is speculative execution allows us to reduce the quadratic phase of seminal work such as PBFT. And of course, we look at this experimentally. So now we're able to scale to 32 replicas. That means 32 copies of the data, 32 redundant copy of the data, and still outperform state-of-the-art and PBFT by over 40%. And we looked at not just the classical seminal PBFT, but also look at the more recent protocols such as Hot Stuff, which is developed by VMware and now is the core of the Libra and Calibra at Facebook, and also Ziziwa, and a form of a fault-free protocol, meaning that the protocol is really designed when there is zero fault in the system, and it can really outperform. But as soon as you add a single fault, inject a single fault, whether it's malicious fault or a benign fault, then the protocol really suffers, which it's very innovative in its design. However, in a practical setting, especially as you scale to so many nodes, one would expect that there might be at least a failure. And so these type of flavor of the protocol that looks at fault-free case are a little bit at disadvantage. So we've also been kind of extending our POE and sort of asking the question, well, we have reduced the phase of support and you only have that single support phase, but can be linearized and it's supposed to have a quadratic communication. And again, now we're using advanced cryptographic toolkit such as threshold signature in order to linearize it. So in addition to having an election commissioner, we could appoint either the commissioner itself or yet another node to gather aggregate the endorsement result, and then on behalf of the endorser, just send the aggregated result to each endorser individually. And it can do that reliably, and again, by using cryptographic technique. And this is something that other protocol like Hot Stuff, SBFD, sort of is becoming in a standard toolkit that a lot of BFT protocol now utilizing in order to convert a quadratic message complexity into a linear complexity. And that's something that needs to be applied for every phase of quadratic complexity you have. If you apply a layer of threshold signature, you can get that linearized. So it's an interesting technique that it's been used in the community. And so we looked at how do we apply it and also leverage from that optimization as well, too, in addition to the core speculation novelty of the POE itself. So now, so far we talked about looking at a single election and how do we reduce a phase, how do we improve it, how do you linearize it, and that has been the focus of POE. But now, as I said, we are been looking at these meta protocol, this new kind of paradigm. And the basic question that my students, Suyash Gupta and Yella, have been sort of raising is that, what if on the same world state, on the same data, we can allow having multiple elections happening in parallel and independently? And that really allows us to scale the whole overall consensus. And so in doing so, we've developed MultiBFT, which is a weight-free meta protocol, and its intention is to designate multiple voter or the multiple endorser as primary. Essentially now every replica will have put a hat on that acts as a replica, but it also acts as a primary and election commissioner. So we have multiple election commissioners that are working in parallel together. And so when we're running these parallel consensus, the essential point is that they're going to be run independently with minimal coordination among them. So graphically, so we run parallel election to kind of getting an endorsement for a particular transaction, and the local consensus itself can be plugged in any type of BFT protocol. So it doesn't necessarily have to be specific one. So, and that makes it, gives it the property of being a meta protocol. And then once each election is ran in parallel, then there's a step of the unification to ensure that every replica is aware of the outcome of all election in terms of the ordering of the transaction. And once the unification is completed, then the execution can take place. But the interesting thing is that the parallel consensus running these multiple elections can continuously run, and in a delayed form, the unification and execution gets completed as well. So by doing so, now we can prove this weight freeness property, meaning that we can guarantee that we always continue to make progress, that at least one of these electioner commissioner will succeed and continue to make progress on our ordering task. And that's the sort of the core and the essence of a consensus protocol. So in a more sort of a detail, we run the parallel consensus. There is a unification to make sure everybody is aware of the outcome of the consensus if they're not so already. And once everybody's have that awareness, then the execution can be done. So the unification is, in a sense, as a mechanism to delay the execution to a safe point, while the ordering is continuously happening in parallel, independently, and in the background. So the theoretical aspect of this was published last year at this 2019 as well too. Now, in terms of experimentally looking at MultiBFT in our ResilientDB platform, is we can see we can scale up to 46 replicas. That means 46 copies of the data and reach nearly up to 350,000 transactions per second. And kind of let it give you a point of reference. When we really started this work back in January 2018, our throughput was like 100, 200 transactions per second. And that's a long way from 100 transactions per second reaching to 350,000 transactions per second. And even today, the Bitcoin still remains at 7 transactions per second. So that kind of shows the great progress that my student has been able to achieve in the last several years. And also, we can get 350,000 transactions if there's no fault, but even if up to a third of our nodes fail due to the benign or the malicious failure, we can still scale nearly to 300,000 transactions per second, even at that level of failure. That means really demonstrating the resiliency of the protocol in presence of such a massive number of failures, which is like a third of the system is failing. Now, kind of asking this question of the meta protocol, so we said, okay, we're going to start looking at a single election. We do a speculative execution, reduce the number of phases to run a single election. Then we look at MultiBFT. How do we now have parallel and independent election happening at the same time on the same data? And now the question is, maybe also an observation of how the election is done in the real world, is that you don't have a single sort of a commissioner looking at all the votes. And for example, in the US, every state or every city, they do the local election and the result gets sort of aggregated and sort of pushed until at the top you find out sort of the final outcome of an election. And this is the kind of asking how do we do this computationally? And of course, consensus is a very powerful tool. So you can always run the consensus on everyone involved and reach that final goal, but it's too expensive. I mean, it's really exhibit multiple phases of quadratic computation. Of course, you can optimize it, but that's what the basis of it is. So now the question is, what is the minimum amounts of computation and communication is needed in order to reach the global decision without running a full-fledged consensus. So again, this meta protocol, this GeoBFT, we're running a BFT protocol locally, so local election is happening in parallel and independently in every region, in every cluster, in every data center. Now we want to be able to achieve a global ordering of these local election through linear communication, as opposed to the expensive quadratic communication. And we can prove optimality of the result as well too. And so a sort of a commissioner in every region will develop, create this certificate, and with linear communication, it informs other regions in the system. And so that's the sort of the basis of the protocol, which is with the optimality also proved as well. So again, graphically, we do local election, and then with minimal communication, the outcome of the local election is propagated globally. And so this work, it appeared at VLDB 2020. Well, the work is already published in the proceeding, but the actual conference and the presentation is going to be later this year. And in terms of, again, we always looked at not just a theoretical, but we also look at practice and the implementation. So in ResilientDB, we see that we can scale to 6 countries, 4 continents, and we can still achieve nearly 60,000 transactions per second. At that global scale, we can still do 60,000 transactions per second. And we can also scale all the way to 60 replica, again, 60 identical copy of the data, and be able to still maintain nearly up to 60,000 transactions per second. Now, looking at a more theoretical side of this, so we kind of already alluded to the problem of how do we do this aggregation of the global decision, or creating the global state based on the local state and the local election that is happening in each region independently. Now, we can now formalize this as a primitive operator, this global communication. And the problem we formalize, and this is a work Yella Hellings, is that we call the fault-tolerant cluster sending problem. So now this is the problem of sending a message from one cluster to another cluster reliably, where one cluster could prone to crash failure or even Byzantine failure. So how do you communicate reliably between 2 clusters when there is possible of either crash failure or Byzantine failure in each of them? And so cast this theoretical question, and within established lower bound complexity, again, we look at 2 classes like Paxos or RAF type of protocol that only support crash failure or can tolerate crash failure, or PBFT, PoE, MultiBFT protocol that also can sustain and Byzantine failure as well too. And again, we showed we can do this. It's only required a linear message complexity in order to do this communication, as opposed to run a full consensus protocol on all the participating nodes. So again, on the figure, you can just have everybody participate in a single giant consensus, and sure, that's correct. You can get safety and liveness correctly out of that, but it's not really needed. So we can now do local consensus, full-fledged consensus locally, and the cluster sending communication. It ensures reliable communication with substantially less amounts of communication that needs to go across continent or across countries. And in terms of kind of give you a little bit of intuition of a variety of formalization to show the lower bound, one is that we developed this bijective function, and kind of asking the question, if we select a pair of nodes, one node in the cluster C1, one node in cluster C2, how many of these pairs do we need to appoint to send messages to another node in another cluster in order to ensure that the reliable communication can take place, that reliably both nodes in cluster C1 and C2 are both benign and honest node and are not failed. And for example, here, as you can see, the red dot, the red boxes are the malicious or the failed nodes, and we want to be able to ensure that at least there is one communication between two nodes that are not malicious. And again, now we study the theoretical underpinning of this model, and then we show the optimality and the lower bound and the linear complexity of this. So, and this was also a piece of work that appeared in DISC 2019 last year as well too. But in the last few months, we asked, can we do better? And in doing so, we really started looking at the probabilistics. So can we do a probabilistic cluster sending problem? And the aim is, can we push the lower bound results from quadratic of a consensus, we came to linear of CSP, cluster sending problem. And now can we do constant time on the average case? And now conceptually, one way to kind of allude to the main idea is that we talk about these bijective sending, these pairs in the last slide. And we said we have to choose minimum number of these in order to ensure that a reliable communication happens. But now we ask, can we pick one pair of these one at a time? And then ask, how many of these pair do we need to select in order to ensure that finally the communication is going to be established, a reliable communication? And so now we're looking at all possible permutation and combinatorial aspect of this problem. And we had to actually devise new mathematical toolkit in order to do this, this analysis. And the result is very powerful. It says on the average case, at most 4 steps is required in order to do the reliable communication. Meaning we may pick the first pairs and we are unlucky. One of them, for example, in the figure as a red node, and so that's a faulty node, so that communication will fail. But the second choice, we get lucky, and both nodes are honest node, and the communication reliably happens. And on average, irrespective of the size, there's only 4 of these. 4 of these is required in order to establish that reliable communication. And of course, the step of sending is more complicated than just sending from one node to another. The local consensus needs to happen in each in order to verify and validate the message that is being sent and the acknowledgement of that message from the remote cluster. So that's part of that step. But then the essence, what needs to go geographically, needs to go across continent, across the ocean in terms of the message latency, that now we can do it in a constant number of steps. And that's the sort of the power of this new theoretical foundation that we have built around this very basic primitive problem of sending message from one cluster to another cluster in a reliable way. So now, looking at another theoretical primitive is that so far we've been talking about every replica, every endorser to be part of consensus. But in practice, there is also a possibility that there are entities that they don't really want to be participating in the consensus, but they want to be able to run analytics on top of the state of all this consensus that is happening. They want to run the analytics on the data itself. So essentially, they have a read-only behavior. So they want to run your SQL analytics, your data warehousing, your AI, your deep learning, your machine learning. So they need to know what the current state of the data is, but they don't really want to, in order to get that information, they don't want to participate in the voting. They don't want to participate in the election. They only wanted to see the outcome of this election that is happening. And of course, they wanted to see it in real time. So now here we formalize another basic problem, which we call the Byzantine learner problem, in order, how do we inform these read-only workloads, what is the current state of all the election that happened so far. And again, so in doing so, we introduce a delayed replication algorithm, which utilizes information dispersal, information coding, network coding techniques, and to allow us to support coordination-free and push-based communication with minimal number of messages. So every replica that participates in the delayed replication to inform these read-only workload, they can do it independently of everyone else, and they only need to send just a subset of the data, just a chunk of the data. And that allows us to get to that linear message complexity. So again, overall, we have our consensus that receives the update and the right transaction, and through the delayed replication, the outcome of the consensus are pushed into the read-only workloads. So now, in terms of a more theoretical sort of view of this, of what's actually going to happen, there will be a lag. There will be a few rounds of delay. So, because after every round or after several rounds, these replicas start once they have essentially a batch of committed transaction or batch of decided election, they start chopping them up and start sending chunks to these read-only workloads. And every replica will do that independently. They send their chunks into the read-only workload. And once the read-only workload are able to get all the necessary chunks, they can go ahead and now reconstruct. And once they reconstruct, now they see the current state. So they could be a few rounds behind, but they're further, and it's still in the realm of being real time. And now, so in terms of the complexity, we'll look at how much messages need to be sent from every replica, and how much data needs to be received by every read-only workload. And then the other one is, how do we now reconstruct? What is the decoding step? So we can really minimize the amount of information that is being passed, but in terms of the decoding and the reconstruction of these chunks together, we may end up having a combinatorial problem, which would be computationally not feasible to solve. But by just adding a little bit of metadata as to what we send, so going from just sending linear amount of data, we'll just add a log n overhead to that message that being sent. Now we can do the reconstruction step in a linear time, basically very fast. And we're doing so by using, again, Crypto Toolkit. We particularly use Merkle tree in order to allow the reconstruction step to happen much faster and still to be very close to the linear plus the log overhead of the metadata due to the Merkle tree that we need to send. So the last piece of work that I would like to share, and also this delayed replication, just make final note on that, is was published earlier this year in ICDT 2020, and this is one of the leading theoretical database conference as well. The last piece of work that I'd like to share is that what kind of as in the last 3 years, we've been developing and building blockchain fabric. And we've been doing so really from a database perspective. And the database perspective is also not just theoretically oriented, algorithmically oriented, but it also practically oriented. And as you see, the database, the relational system, has been arguably one of the most important components in the software stack. It is the backbone of every enterprise, because what enterprise can do if they cannot store and retrieve their data efficiently? So the database has been the leading force and providing automation into the enterprise in the last 50 years. And in doing so, they have to build sophisticated system-centric view of how do you build and deploy these large-scale systems. Of course, many of these lessons are also we can take from operating system as well. These are two, I would say, one of the two most important piece of software that have been developed over the last 50 years or so. So, but then in contrast, when we look at the work in distributed computing, and especially in the blockchain or in the consensus protocol, oftentimes the theoretical aspect is very rich. But when it comes to the system aspect, they lack the maturity that you would see in system-oriented community. For example, oftentimes the prototyping or the evaluation is either just a simulation, not an actual real deployment, or it's like a single-threaded implementation of the proposal. So this single-threaded design, it's really limiting, and it doesn't really capture the full complexity of the system or the full capability of the system, especially now that we enter this era of multi-core and large memory. It leaves most of the resources that is available to us underutilized. And the other aspect that we looked at in terms of the system-oriented view of building a blockchain fabric is that how do we now look at ordering the communication? How do we develop more sophisticated transport layer that it doesn't necessarily need to do this every communication, every message is sent in a stepwise fashion. It can really create pipelining and out of order messaging and sort of add a little bit of a correction in the ordering at the endpoint, but then it really speeds up sending these messages to really allow the full use of bandwidth of the underlying subnetwork as well too. So that's another thing we've been studying. The other one is really decoupling of the ordering of the execution. The election outcome doesn't necessarily need to tie directly with the execution of what was agreed upon, in the order in which they were agreed upon. This is something we kind of already alluded to in MultiBFT and to some extent in PoE. And again, that is a central design point, architectural point that we wish to share with the community. And of course, the use of off-chain, on-chain memory management using techniques, buffer pool techniques, including the persistent technique that have been developed in the last 40, 50 years in the database community and also in the operating system community when it comes to memory management, memory allocations, and all the synchronization and memory issue that centers around that. And also looking at expensive cryptographic practices. For example, using digital signature, or using MAC. Digital signature is a more heavy computation, much more heavy compute intensive. It allows simple forwarding. It may simplify the protocol itself, both the fault-free and the fault case of the protocol, the view change aspect of the protocol, but it's computationally expensive. But now can be simply use a much lighter protocol like using MAC in order to do reliable communication. And you can provably show some of the protocol that we have, like PoE or MultiBFT. We can actually entirely just use MAC for every single case, both for the faulty case and the view change aspect. And that's something that not always obvious from the theoretical perspective in the literature, but this is something that we've done both theoretically and also experimentally. And experimentally, we can see substantial performance benefit when we try to avoid digital signature. Of course, there's other interesting thing. We talk about threshold signature. That even add a little bit more complexity. At least today, we have military-grade implementation of digital signature, but for threshold signature, that's kind of lacking. And well, theoretically, it's an interesting idea in order to linearize the communication, but in practice, it still remains as an open problem. First of all, what is the real overhead of doing that? And how about, can you do it in an accurate way that is really have that gold standard of being military grade in terms of its implementation and deployment. And finally, we've been looking at smart contract. That's the window to the outside world in order to be able to utilize it. And so we're using a Turing complete language such as Go in order to express our smart contracts, and also looking at code generation, pre-compilation, and all those toolkit in order to enhance and speed up the execution of the contracts. And again, so this together really comes as an architectural and implementation lessons that we have learned through the lens of databases over the last few years. And so that came together in a paper that will be presented later this year at ICDCS. And in doing so, in ResilientDB, we have developed this very sophisticated pipeline. So the runtime is multi-threaded, has multiple stages. Every stage has multiple threads itself. Things are running in parallel and independently. Then that really allow us to go beyond sort of just a basic single-threaded execution. And in doing so, again, we pose this very fundamental question. And that is, can a well-crafted system based on a classical BFT protocol even outperform a modern protocol that was proposed 10 or 20 years later? And this is really to have that system-centric design when we build a fabric, as opposed to have a limited protocol-centric view. And that's the difference of, for example, having this sophisticated pipeline of the execution versus, well, just I'm going to run a single thread. And here we can see we can actually do that. So comparing ResilientDB, its PBFT implementation compared to Ziziwa, which is a protocol that is designed for fault-free case, and there's no fault in this graph, is that we can achieve with the sophistication that we add to the system, we can outperform this modern protocol that one could say is an optimal protocol when there is no fault by a factor of 2 or higher. And that's really bringing the point is the system-centric design. It is absolutely crucial when we're building these blockchain fabrics. And with that, I'd like to come back, revisit our resiliency exercise, and then continue to go back to our graduate student experiment. So looking at the third hike that we went, so this is one of the hardest hike that I've done myself on a single day, and which is Monolithic, also in Lake Tahoe. This is only 12 miles, but it's a 4,000 feet elevation gain, and it really happens in a few miles. And at the summit, you reach 10,000 feet, and the oxygen level, it's really different at the 10,000 feet when you're at sea level. So the breathing is going to be a bit difficult, and the body, it takes a toll on the body itself. So this is a picture that I took sort of pretty much close to the peak. And it's simply astonishing, and it brings an awe when you look at it. You see this tree standing, resilient and stable in such a harsh landscape, all by itself, but it stands. And there you also see my PhD student, Sadoghi, is also in awe, looking at the magnificence and the resiliency of this tree, and he himself is standing. And this is toward the end of the hike, and it again shows even the resiliency in him. So it was just a very beautiful moment and to capture, and so had the opportunity to capture it. It's just amazing looking at the resiliency. And of course, we made it to the top, and this is the peak. That's a 10,000 feet peak that we're still smiling, and we're all happy, and it's just very meaningful having these trips and at a personal level with my student. It's very meaningful to me, and I really appreciate, and it's something that I personally cherish very much. And of course, the next day the next day was a very different story. For the next few days, I think they had difficulty even getting off the bed because of the sheer soreness in their body, but definitely worth it. The experience remains. And again, to sort of bringing a conclusion to this resiliency theme, we looked at resiliency protocol, we looked at resiliency in building this protocol that allowed the student become more and more resilient. I've also been offering what I consider as fostering resiliency through yet another method. And this is by offering stress management and well-being courses at UC Davis. This is something that I started January 2019. Currently, we are offering 3 courses every quarter, and one is being offered by computer science graduate department, and 2 other are offered as first-year seminar, which is open campus-wide to the 35 and 40,000 students at UC Davis. And this is based on a meditation technique. It's a heart-centered meditation technique called the Tamarkuz method that I have personally been practicing for the last 12 years. And it has brought a level of stability, resiliency, creativity, and joy. And it was my pleasure to be able to pass that on to our students. And we already know that in the United States, 1/3 of college students and university students are suffering from mental illness. These are diagnosed mental illness for 1/3 of our students. Graduate students are even suffering at a higher level. So it is an epidemic, if one may say, that it's important to be able to foster that resiliency. And recently, one of our courses has also been covered by the California Aggie. This is a student-run university that look at one of the courses and done a number of interviews with myself and the students on the course, which we title Becoming an Extraordinary Human. So it has been a wonderful experience teaching the Tamar course to our students as well. And with that, I would like to thank you all for listening, and I hope you enjoy the rest of the Reimagine 2020 conference. And so on the behalf of Expo Lab at UC Davis, we thank you all, and we hope that you get the opportunity to download and fork ResilientDB and join the community in building the next generation of blockchain fabric. And with that, again, thank you very much and have a great day, everyone. Thank you.